Yeah, so already short introduction of who I am. I'm just going to explain a little bit who I work for. So I work for the company Dekimo. We were founded in 1987 as an electronic subcontractor. So we don't have any products of our own. We are a service provider, and we have about 400 employees, of which 95 is engineering. Now, the Belgian division of Leclanché, which is a battery manufacturer, joined us in 2018 in the Turnhout site. So that's why we have quite some knowledge on batteries. Yeah. We do all BMS designs in cooperation with the Leclanché, who has experience in all kinds of applications with batteries and BMS systems. Okay, so what are we going to see today? I'm going to explain a bit on how a battery works, some basic stuff. Then I'm going to show you what the difference is between a battery and a lithium battery, so what makes a lithium battery special, and then a small introduction into battery management systems. Okay, now a battery. What's inside a battery? Now, there was a scientist, Alessandro Volta, in the 18th century, and he did some experiments with some metal plates. And these metal plates, these are zinc and copper plates, and he stacked them on top of each other with a paper in between, which is soaked in a salt solution. And he stacked them on top of each other. Now, what happens here is you get a chemical reaction. And you get a chemical reaction between the salt water, which is the electrolyte, and the zinc plate. And this oxidizes the zinc, which creates negatively charged electrons. The copper plate also reacts with the salt water, and this produces positively charged ions. So you get a voltage potential between those two. If you connect a wire between them, you get a current, because the negative electrons go to the positive side. Now, just as a side note, there are two ways you can talk about an electric current. And we can talk about the conventional current flow, and you can talk about the electron flow. So I'm talking about the electron flow, where the electrons go from the negative to the positive side. Just as a side note, so you can see why the current goes in that way. If you connect then a light bulb to it, then you provide power to the light bulb, and it will work. Now, for the people with children at home, this is a fun experiment you can do. If you take some lemons and you put a nail and a piece of copper inside of that, so the nail is zinc coated, and you put a copper piece, for example, a 10 euro cent piece, for example, and you connect them together, you actually have a battery. So it's a fun little thing you can do with the kids at home to show, hey, I can make a battery. Now, fortunately, with technology advanced, so I don't have to power my electric vehicle with lemons. So we advanced a bit there, fortunately. And so one of the things they did is they replaced the electrolyte, which is a liquid. They replaced it with a paste. And that's where the name dry cell comes from. So everybody knows those batteries on the top right-hand side. So those are dry cells. Those are called alkaline batteries. Now, I've talked about a cell and I've talked about a battery. Now, just to be clear, when you talk about a cell, you talk about the copper and the zinc plate, so just one cell. If you talk about a battery, you're talking about multiple cells together, either in a series or in parallel, depending on you want more current or you want a higher voltage. Yeah. All right. Now, as for cells and batteries, there are two types. You have primary cells and you have secondary cells. The difference between them is primary cells, they cannot be recharged. So the redox process that you just saw, so the reduction and the oxidization of the metals is irreversible. That's a primary battery. And you have several types that you all know. For example, the zinc manganese batteries, which are the alkaline batteries that you use in toys, remote controls, stuff like that. You have the silver oxide batteries, so that's the button cells that you use in hearing aids and also stuff like that. But you also have lithium primary cells, so they're not rechargeable. On the other hand, you have the secondary cells. They are rechargeable, and you have the lead-acid batteries, which you know from cars. They can both be wet cells and dry cells. You have the nickel-cadmium batteries, which are capable of delivering relatively high currents. you have the nickel metal hydride batteries, which have a higher capacity, and then you have the lithium ion battery. Now, all these batteries, they work on the same principle, and so it's always a redox reaction between two metal plates. But what makes the lithium ion battery special is that the metals used in a lithium ion battery, it's a lithium metal, and the lithium metal is a very lightweight metal, which makes the batteries very suitable for mobile applications. Now, when you talk about lithium or lithium ion battery, it's not like this, there's just one type of lithium ion battery. There's lots of different types, different mixtures that they use. And the reason why this is because they try to improve the batteries in certain fields. For example, you want to have a battery that can be charged a lot more. You want a battery that can withstand higher temperatures. You want a battery that has higher capacities. So they never have just lithium. There's always a mixture of something in there. But it's always with lithium metal. And you have some different types here. And you can see, if you look at the overview here, I have an overview of some chemistries, and you can see what the upsides and downsides of some of them are. For example, if you look at an LCO battery, is something which is very popular and used in, for example, laptops and mobile phones. And if you look at that, it's a battery with a very high energy density. So if you look at the second line, it's a battery with 250 watt-hours per kilogram. So it's a relatively high energy capacity. The cycle life is okay, but it has a relatively low thermal runaway. So that means if the battery goes beyond 150 degrees Celsius, it becomes dangerous. If you look at the other side, for example, LTO batteries, if you look down there, you can see the cycle life is much higher than, for example, an LCO battery. It's much safer. It has a much broader temperature range, so it seems to be a much more capable battery. But it only has 80 watt-hour per kilogram, so it needs to be larger. So for a cell phone, that's not exactly what you want. Yeah? So that's why you have all these different chemistries in lithium batteries. There's a little graphical overview so you can see where they focus. That's basically the same as I just showed you in the previous slide. Okay, so I'm going to take a small example here. This is just one of the chemistries. It's a lithium iron phosphate battery, just to see how this works internally. Now, basically, the battery still works the same as the Volta cell. So what you have inside there is still, you have a cathode, you have an anode, you have an electrolyte in there, and you can charge it and recharge the battery. The only special thing is that there's a lot of lithium contained in there. One of the problems you have with lithium is a metal that is very reactive. So you cannot just use an aqueous solution for the electrolyte. So it has to be without water. So that's why they use a lithium salt. And this lithium salt that performs the function of the electrolyte. Okay, if you look at the electrical properties of a battery, then you can see you have something called a discharge curve. So you know that if you take a battery and you have a battery of, let's say, 3.2 volts, that's the nominal voltage of this battery. If you look at the actual voltage of the battery, it will depend on the charge you have in there. And if you look at this discharge curve, there are three regions that you can define. You have the first region all the way to the left-hand side, where the capacity is still 100%, where the voltage is relatively high. Then you have a large part between, let's say, 90 and 10% of the battery where the voltage is relatively constant. And then you have a part where the voltage drops off very steeply. So those are the three regions you have in battery voltage. If you want to prolong the lifetime of a battery, then it's best to stay away from the complete ends, so the extremes. So don't go all the way up to 4.5 volts or something like that. Don't discharge it too much. It's bad for the lifetime of the battery and could even be dangerous. Now I have different discharge curves, and what you see is that the curve. The voltage depends mainly on two things. It depends on the current that you draw from it, and it depends on the temperature. Now, the current you draw from the battery makes the voltage just a tad lower, but the curve is still, well, in the same form. But if you look at the temperatures, with lower temperatures, the voltage drops significantly. So that's what makes it sometimes a little difficult to determine the state of charge. The state of charge is what you see on your cell phone. My battery is 20%, 30%, 40%. So that's what makes it a little hard to calculate it, and that's what makes a BMS actually difficult to make. On the other hand, you have the charge curve, so you want to charge your battery. And in the charge curve, you have two regions that you can see. The first region you have is on the left side from 0 to 80%, where you charge the battery using a constant current power supply. So you push, for example, 1 amp, 2 amp, 10 amps inside in the battery. And the battery of the voltage will rise until the capacity is up until somewhere between 70 and 80%, depending on the chemistry that you're using. From that moment on, the battery voltage will be at the maximum voltage allowed, and you have to charge it with a constant voltage. And you put 4.2 volts on the battery, and then you will see the current drop off slightly because you cannot push too much energy into the battery. And once the voltage drops between, the current drops between a certain level, then you have to stop charging to avoid overcharging the battery. Okay, now there are some safety risks I want to talk about in a battery, and there's one of the things you have to keep in mind is the thermal runaway. This is one of the most one of the biggest dangers in a lithium battery. And the reason why you can get a thermal runaway is because of either an internal failure, a bad cell, that can happen, or you can have external factors for a thermal runaway. One of the things you should, for example, never do is shortcut the battery or puncture the battery. Because if you puncture the battery, you will create an internal short circuit, which will cause a thermal runaway. And you will see that most faults that you can have in a battery will result in a thermal runaway. So it's very important that you do not abuse a lithium cell, and that's the reason why you have a BMS. For example, here, if you have an overcurrent or you short circuit the battery, that can result in a thermal runaway because the battery gets too warm. If you overcharge the battery, then you can also get a thermal runaway if you try to push too much energy in the battery. If you undervolt the battery, so that means if you draw too much energy from the battery, that in itself is not really dangerous, but it will damage the chemical structure of the battery. So if you recharge the battery again, then you can get a thermal runaway. So that's one of the things you should also never do. Never draw too much energy from a lithium battery. So are lithium batteries dangerous? No, they're not dangerous if you use them correctly. That's important what you have to do. You cannot use them outside of their comfort zone, and that's why you need a BMS. There's two types of BMS that you can use. It's either a PCM or a BMS that you can use. Now, a PCM is a protection circuit module. That's not a full-fledged BMS. I'll talk about that in the next slide. And a BMS is actually something that manages the battery completely. Now, if you talk about a PCM, that only takes care of the basic safety of a lithium cell. Yeah? So a PCM just prevents your battery of being overcharged, over discharge, short circuits. That's what a PCM does. Yeah? And you can see those PCMs if you buy, for example, an 18650 cell. So it's these round cells. You can see that some cells are just a tad longer than other ones. Now the longer ones, they have a PCM inside. So it's located here on the top of the battery. That's where the PCM. So it's a very small circuit board. If you have those pouch cells that you have there on the left-hand side, you can see a small PCB on top of the battery. So that's the PCM used in that cell. Yeah? Now, if you talk about a battery, as I said, a battery consists of multiple cells. That means that you can have multiple cells stacked together, either in series, in parallel, and then you have a battery. And then you need a battery management system. And the reason why you need this battery management system is that because you have to monitor a lot more. Now, most of the things that a battery management system does is exactly the same as a PCM. So it prevents the battery from being used outside of the safe operating area. If it is used outside of the safe operating area, it will protect the battery by either disconnecting it, for example. But it will also give you a lot more information on state of health, state of charge, the temperature, the cell voltages, and stuff like that. And it will also try to increase the performance of your battery by, for example, activating heating or cooling systems for your battery. You have to understand that if you make a battery that consists of multiple cells, and you take, for example, 10 cells, you put them in a casing, then the internal cells, they will become hotter than the cells on the outside. So you have to cool those cells better. And you have to balance the cells. Now, balancing a cell means that you also always have to make sure that the level of charge of your batteries is almost the same in a battery. And if you don't do this, then this is what happens. If you have an unbalanced pack, so that means you have several batteries just connected in series together, and it'll work. It's not a problem. Yeah. But when you start to discharge this battery, then the first battery will discharge until, let's say, 10%. The second battery will go to 11%. Next battery will go to 9%. Okay, let's just recharge it again, and then you start recharging it. But if you recharge it, then the battery which was discharged to 11% will be charged to 100%, but the one that was discharged to 9% will not be at 100% anymore. And this is where you get drift. So at the end, your battery pack will look like something like this. Now, this is a problem because if you saw in the previous slides, the cell voltages will differ. So that's one of the issues. Next issue is this is a battery pack you cannot recharge anymore, because if you look at cell number two is still almost full, and you cannot overcharge a battery. You cannot do that because that's dangerous. It will get a thermal runaway. If you look at the last battery there, it's almost depleted. So that means you should charge it, but well, you can't because the second battery is already charged. So that's a challenge. That's a problem, and you have to solve that by balancing your battery pack. And the way you can balance a battery pack, again, there's two ways. You can do it actively and passively. And if you do a passive balancing, then actually what you do is you can just connect a resistor in parallel over each cell in the battery. And that seems like a lot of waste of energy, but in practice, it's a very small amount of energy that you're going to waste. And what you do is when you have a battery pack which is being discharged and you charge it again, then the cells that have too much charge, you can discharge them over this internal resistor. So that's how you do passive balancing. And this is the way that let's say 95% of the battery packs are balancing it. This is a practical example of one of those ways you can balance it. Now this is what is called an AFE. So it's an analog front end, which is a part of a BMS. It's not a BMS. It's a part of a BMS. And what you can see here, yeah, laser pointed doesn't work. I tried. Sorry. So what you can see here is you have a MOSFET and the resistor over there, and that's the MOSFET which is going to discharge that cell slightly to get the charge under control. And what the AFE does, it can discharge every single cell separately in this battery pack. Then you have the chip, and then you have a communication interface. And what's often used in battery packs is that you use an ISO SPI bus. So an ISO SPI is basically an SPI bus which is galvanically isolated to prevent those different voltages. Because what you can do if you have a battery, and for example with 12 cells, you cannot go up to a certain voltage. But if this is not high enough, you have to put more in series. So what you do is you use multiple AFEs together. So you can put all those batteries in series, and then you can connect them together and communicate with them over the ISO SPI bus. Is something I need to explain in a little more detail? Huh? Well, you will get the presentation so you can see the exact part numbers which are being used. It's just a screenshot from the data sheet of linear technology. So you can look up those schematics. Nothing really fancy. Okay, so this is how the analog front end in a BMS works. Now, obviously, that there's multiple chips you can use for this. This is just one of the examples that we've used in the past. Then you can also do active balancing. Now, active balancing is not something you do very often because it's relatively complex to do. But in an active balancing, what you do there is you actually transfer energy from one cell to another cell. And the way you can do it is, for example, by storing energy in a coil or an inductor, and then you transfer it to a second cell in a battery pack. And there's some examples you can use. For example, TI has some chips that actually can do the active balancing. So it has some external circuitry here, which comprises of a coil. And what you do is you transfer the energy to the coil, and you discharge the coil into the next cell or where you want to transfer the energy to. So it's a relatively complex process to do, but it's possible. Okay, now, one thing I need to make very clear, which is a common mistake. A BMS does not regulate anything. A BMS only monitors and gives you information and protects the battery. Yeah? It doesn't regulate anything. So it provides information to the consumer, being a bus, a car, boat, train, plane, whatever. So it provides information to the consumer of how much energy can you draw from the battery pack. And it provides information to the charger saying this is how much energy you're allowed to put inside the battery. But it does not regulate anything. Okay? It just shuts down the battery if something goes wrong. Okay? Good. Now, as for a BMS system, what's in there? Because we talked about a few things. We talked about cells. We talked about batteries. So a battery is multiple cells inside one casing. We've talked about the EFE. So that's this part here and this part here. So this is the analog front end, and this is where the measurements are done. Now these measurements are done by a microcontroller, and this microcontroller, there is an algorithm inside of there. And this algorithm will try to determine all the parameters like state of health and a state of charge. As you've seen in the discharge curves, it's not very easy to say, yeah, my cell is, I don't know, at 3.2 volts, so it's at 70% of charge. It doesn't work that way. You have to take into account the current that's going in or out of the battery, and certainly the temperature, which is very important. And then you have the protection. So on top of there, you have the contactor or the MOSFET, which will enable the battery to deliver power. You have a fuse, which will blow if you short circuit it. And you have the current sensor in the bottom to sense the current, which is drawn out of the battery pack. Okay, now battery pack designs. If you look at battery pack designs, now the term battery is used loosely. So I've said that a cell is a single cell, a battery is a collection of cells. In practice, most people talk about batteries, even if it's a single cell. If you have a single cell, a battery pack, usually what you have is a PCM, which I talked about a few slides ago. And in this PCM, there's just the basic electronics needed to protect the battery. So you have a very simple circuit. You have the fuse. You have the MOSFETs to turn the battery on and off. And then basically, there's not much more in there. So that's a PCM, very simple circuit. Then you have a BMS for low voltage battery packs. Low voltage being less than 48 volts. Now I've talked about that also a few slides ago. So what you have there is the fuse for protecting the battery. You have the current sensor, the microcontroller, EFE, and so on. So that's a basic the build-up of a battery management system for a low voltage pack. And then you have the high voltage battery packs. Yeah. So as you can see in a high voltage battery pack, we've talked about the EFE, where you can have, in this case it was 12 cells. But with 12 cells, you're not able to reach very high voltage. Yeah? So what you do is you have a sort of a slave BMS. And this slave BMS, this one will monitor this battery pack here. Yeah? So this is one battery pack which can work on its own, and it will communicate using, for example, a CAN bus inside of the battery pack. And then you have this battery pack with this battery management system. You have multiple of them connected in series, and they all communicate with a CAN bus to the master BMS. And this master BMS will monitor the complete battery pack. So that's how you make a high voltage pack. And then basically for the protection, that still stays the same. You have the current sensor, you can turn the battery off, you have the fuses, and then on top of there you have the contactor to turn the battery on and off. Now the reason why you have two contactors there is actually because you're talking about very high voltages and you're talking about extremely high currents, several hundreds of amps that can go there. So if you would turn the battery on and you would charge external equipment, so that has coils or capacitors in there, you will have an extremely large current going out of this battery pack, which is also not allowed. So that's why you have two contactors there, one with a resistor and one without a resistor. So first you connect the contactor with the relay, charge the equipment, and then you bypass bypass the resistor, so you don't lose energy in that one. So that's how a high voltage battery pack basically works. Then you have the multi-string batteries, and this is mainly used in energy storage. So you have these large containers that you use for energy storage, and there you have all these high voltage packs also connected to the same lines. And there it's very important if you connect them to the main power line, that you always make sure that they're about on the same potential, because if you don't, you get a lot of current draw. But that's basically how you make these high voltage packs. Oh, okay, it was a little delay. Sorry. Okay. Yeah, yeah. Telex asked me to hurry up a little. I didn't go too fast. Okay. Right. Are there any questions? Yeah.
Yeah, when you talk about high voltage, what voltage range do we have to think about?
In practice, Wim. Yeah, my colleague joined me because I'm just a project leader. Wim, my colleague, is an actual developer who works for the Leclanché products, and he has the more experience on that one.
Typically, they goes to 1000-volt DC, but yeah, they can also go up to 1500-volt DC, but that's mainly the highest voltage they go up for a DC.
How many?
Ah.
Active balancing is only to the next battery cell.
Yeah, yeah, it's only to the next battery cell. So if you have a very unbalanced pack, well, in theory you will not get very unbalanced because you start balancing from the start. And so you try to avoid an unbalanced pack. So when you do these energy transitions, it's always a very small amount of energy that comes from one cell to another cell. Now the exact algorithms from how they exactly do it depends from chip to chip. But it's actually from one cell to the next cell, so you don't transfer it from cell 1 to cell 10 or something. That's not done.
You tell me which one is the last solution.
No.
I'm sorry to contradict you, but there are solutions today that allows to do that.
Well, that's the advantage of being an emerging technology. There's always always new developments being.
Well, at Vito, we are working on technology
Yeah.
that allows to do that. So active balancing from whatever cells up to
Yeah.
whatever cells in the string.
Okay. All right. All right. Looking forward to that.
In terms of electronics, of course.
Yeah. There was.
How frequent is this for you at Dekimo to have these discussions with customers compared to 5 years ago? Is this something which is daily issue, or is this once a week or once a month? Or
What
these
discussion?
kind of discussions with your customers developing a product,
Oh,
having
yeah.
a power supply, having a
Yeah.
battery system? Is this something which comes up once a month, or is this something which comes up every week, twice, or?
We've been working on that for the last. Wim, how long are you working with us? 6 years.
For Dekimo.
Yeah. yeah, about six years with a team of six, 7 men on full time. So yeah, there's a lot of demand for that.
There are a lot of marketplaces where batteries are needed.
Yeah.
Okay? We tend, in fact, to become completely cordless for a lot of different applications. So we talk about drones, we talk about hand tools, we talk about indeed mobile phones and so on. But it's also related to a lot of new machines that comes to the market and that will work on battery. So there is not only the electric mobility issue, not only the great storage devices that was mentioned by Peter, but there are a lot of devices, in fact, that needs a battery powering for the future. Yeah, included that one.
So yeah, there's a lot of demand for battery applications. Yes.
And 5 years ago you were 2 or 1, and now you're 6. Is that?
Yeah. Well, before Leclanché joined us, for battery applications, actually not that much. So that's of, let's say, if you do 50 projects, then we had like 1 or 2 projects that involved batteries. So it's because since Leclanché joined us that we are very active in this development.
Okay.
So it was either very uninteresting or I was very clear about everything.
Very clear, very accurate.
Okay, thank you. Hey, thanks, guys.
Thank you very much.